Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Ladies and gentlemen, good afternoon, or whatever part of the day you happen to be joining us from. This is a real benefit of going virtual. Hi, I'm Rick Lufkin, Chair of the Cardinal and Gray Society. Welcome to a new generation, a new season of programming for Cardinal and Gray. This is a great relief to be finally restarting again for the year, but not only Cardinal Gray, we also welcome members of the Emma Rogers Society this afternoon. We really do very much appreciate your continued engagement. Looking ahead briefly, the in-person Cardinal and Gray holiday luncheon will be held at the Wellesley Country Club on December 15th. Lizzie Army will be posting an entry in the chat box with a registration link for that right now, and you will be able to register at your convenience. Additionally, spring programming for Cardinal and Gray is currently in the late stages of development. Quite likely, this will also be in person. More to come on that. We are slowly returning to the pre-pandemic world, but with some new twists. Cardinal and Gray is but one important vehicle for connecting alums with the Institute. MIT offers many opportunities for support for and by alumni. A number of today's attendees, including my wife and I, have included MIT in our estate plans and are therefore proud members of the Catherine Dexter McCormick Society, one way of connecting that has special relevance at our stage in life. Following our speaker's presentation this afternoon, you will have the opportunity to ask questions. Please enter them in the Q&A box on your Zoom screen whenever they come to mind. Following the talk, we will endeavor to have Professor Hartwig respond to as many as possible. Once in September 2021, the Spark Toroidal Field Model Coil, a joint project of the MIT Plasma Science and Fusion Center and Commonwealth Fusion Systems, achieved a peak magnetic field in excess of 20 Tesla. This moment ushered in a new era of powerful high-field superconducting magnets for science and industrial applications and enabled a long-sought paradigm shift in fusion energy towards smaller, lower-cost devices. How did this shift come to be? And what technologies and pioneers set the stage for this new era? This afternoon, we will hear the century-long odyssey of MIT in high-field magnet research and share details about the TFMC project and its future. To take us down this intriguing path this afternoon, we will hear from Professor Zachary Hartwig. A Missouri native, Zach is the Robert Noyce Career Development Professor at MIT and an Associate Professor in the Department of Nuclear Science and Engineering with a co-appointment at the MIT Plasma Science and Fusion Center. He has worked primarily in the areas of large-scale applied superconductivity, magnetic fusion device design, and plasma material interactions. He was the principal investigator and project head of the Spark Toroidal Field Model Coil project, a successful 3-year effort from 2018 to 2021 to design, build, and test the first large-scale, high-field, fusion-relevant, high-temperature superconductor magnet. He is a co-founder of Commonwealth Fusion Systems, a private company commercializing fusion energy. He received his doctorate from MIT and his baccalaureate in physics from Boston University. I will now pass the virtual microphone to Professor Hartwig. Zach, you're on.
Rick, thank you so much. It's a wonderful introduction, and I appreciate you going through all the details. Let me welcome everybody to the talk and say it is a real pleasure to be here and talk to the Cardinal and Gray Society. In part, what I want this talk to be is a little bit of a source of pride in MIT's legacy that you all are a part of, and really show sort of how the institutional capabilities that MIT's built up over a century and a half that it's been here is really translating into major impacts into things that we're doing today. So with that, let me pull open my presentation and get started. So what you see behind you is the large-scale superconducting magnet in the center of the screen, sitting in the middle of a test facility that we built here at the MIT Plasma Science and Fusion Center. We're located a little bit off main campus, down Albany Street. And you can kind of get a sense, you see the people here, you get a sense of the scale that our laboratory works on, and really the sense of scale that we are operating in fusion. So this is not exactly benchtop, tabletop science. This is really large scale engineering and engineering science. So this is what we're going to go through today. And so I want to just acknowledge some of the contributors, many names here who've helped me put together this talk. So as always, those of you who've worked in teams, of course, know that, that every team needs a leader, but it's really the people and the individuals who make projects work and ultimately are sort of the source of success. So I always, when I give this talk, we've given a lot of these talks over the last year since testing the coil. I always like to just point out and put, a set of names up here for people who contributed in a huge way to the project. We obviously can't go through all the names, but I do want to thank them. Another person who is not involved in the technical work I'd like to acknowledge is actually Ryan Bucas, a member of the Cardinal and Gray Society. I think I saw Ryan's name in the participant window. And so another reason why, we're here and doing this is Ryan, as many of you probably know, a big proponent in fusion. And of course, part of the reason I was excited to come and give the Cardinal and Gray talk was we actually hosted a group of members. Ryan will have to remind me, but I think it was class of 67. We arranged a whole tour for the class of the Plasma Science and Fusion Center, and they got to see a lot of the things. And it was really a wonderful day and interaction. So I was really happy to be invited here to get to sort of spread our message to a much bigger group of you all. So a lot of excitement about just doing this. So, okay, I was told when Rick and I talked that this is a group who does like to get a little technical. So we are going to get into the details a little bit of what it takes to build sort of a high field superconducting magnet. And so we'll do that. And so this is actually just sort of in one picture, if you like, sort of a summary of what we did in this project. This was essentially, as you heard earlier, a sort of a large-scale project to design, build, and test what was really a first-of-kind superconducting magnet. And it wasn't just building the magnet, which you can sort of see here down at the bottom left. It was actually building the entire infrastructure and test facility around it that was also pretty innovative in order to test the magnet successfully. As you see here, in a pretty tight time frame, a 2-year project. And remember, you saw that picture of the team. Everybody was wearing masks. We actually had to work straight through the pandemic because this was a big hardware project. Time was ticking, and we had to deliver this project to our sponsors, Commonwealth Fusion Systems. So this was a pretty impressive project. And I want to point out this was the culmination really of 3 years of pretty high profile work. So those of you who follow MIT, many of us tune in to MIT's homepage every day just to see what's going on. And so I'll cast back to March of 2018. We announced this idea of starting a private fusion company, Commonwealth Fusion. We raised about 150 million in our first round. And we were basically saying we're going to, develop magnet technology to go and build a compact fusion device. And so we were pretty pleased to make the front page of MIT News. And that was the most read story in 2018. Of course, we had to put our heads down and do a lot of work over the next 3 years, but we came back about a year ago, a little over a year ago in September, and announced that essentially what we promised to do, which was to develop a completely new generation of magnets and really advance the technology. We did it, and the team did it. And so this was a story that was also the #1 most read story in 2021. So, clearly a set of activity that was sort of giving a lot of press to MIT and a lot of attention, which is great. So we've been talking about this project. So essentially we had to, design and build a first of kind superconducting magnet. We'll talk about what that is. But what I wanted to do is actually give the audience a bit of a sort of a comparison. So is there another project out there that happened before that looks a little bit like what we had to do? And there is one. So this is a project that was also a superconducting magnet test. You can see a picture of what a real superconducting magnet looks like. And we'll go into those details in a little bit. But the point here is to actually compare something that was done before to what we were able to do here at MIT. And so if we were to look at the scope of this particular project, this ITER, CSMC project, this was physically a much larger coil, and you can kind of get a sense of scale by looking at this picture. It had very similar sort of magnet operating characteristics, but it was at about almost half of the magnetic field, which is, if you're building a magnet, you want higher field. The time scale that it took to deliver this project was about 10 years. Sort of 2 years to develop some of the fundamental technologies, and then 8 years to do the design, the fabrication, and all the testing. And if we look at who participated in this project, this was about a dozen plus major industries across 3 continents, sponsored by 6 or 7 federal governments. So you see, names you'll recognize: Lockheed Martin, Toshiba, Mitsubishi, Hitachi, and Saldo, which is a big construction company in Europe. This was a huge, decade-long, very expensive effort that did result in a successful coil. But it raises a very interesting question, and it was a question I started thinking about when we concluded the project, and I had a little bit more time to think. And so the question is really, our magnet was smaller, but MIT, along with Commonwealth Fusion and our vendors, essentially executed the same project in almost half of the time, and did everything in-house ourselves with some vendors. We didn't have a Lockheed Martin to participate with us, Kobe Steel, Mitsubishi. We took about 2.5, 3 years. We didn't take 10 years. And a really important point is that when we tested this magnet the first time out of the gate, it worked, and it worked perfectly. And so it kind of raises this interesting question about, how did we do this? How was this team able to come together, advance this technology by something like a factor of 1,000 to 100,000 in terms of some of the key metrics, and to do it, all during COVID and with all the restrictions and supply chain issues that occurred. And so this really helps sort of, I think, set the stage for the talk that I wanted to give to this group today, which is, I know people like to see the technology, and we often hear talks from scientists and engineers about what we did, right? We built this magnet, we put this much current into it, we tested it. But what I wanted to do at this talk was give a little bit of a different sort of look at technology, and sort of ask some questions about not so much what, but more how did we do these things? How did it work successfully the first time? Why were we able to do this? And maybe more important for this audience, I mentioned this is going to be a bit of an MIT booster talk. Why did this project happen at MIT as opposed to happening somewhere else? So I think this is what I really want to get to for the heart of the talk. So in order to do that, I'm going to try to do 3 things over the next about half an hour. I want to try to leave enough time for questions and answers. So what I want to convince you is, first, that high field superconducting magnets enable a much better pathway for us to get to fusion energy sooner, smaller, and at lower cost. We think fusion is an important part of helping tackle the climate change issue, and superconducting magnets, as you'll see, are going to be key to that. I want to then convince you that this new magnet technology that we built and developed here is approaching maturity. We're ready to start using these magnets in fusion devices. And then I want to sort of talk a little bit about this question about why and how. And just to sort of preface the answer, I'm going to talk about 3 things and try to give you a real sense of what these mean: culture, climate, institutional capabilities, and the people that are all part of what we do here at MIT. So to do this, what we're going to do is we're going to look briefly at what are magnets, what are magnetic fields, why is this important to fusion energy. It will take a quick look at what our magnet is, how did we build it, how's it designed, and what does its success mean. But then what I'd really like to do is actually go back about 100 years and trace the long history that we were able to build upon to be successful. So that's what we're going to do today. So let's start by talking about magnets. So I think often when we talk about magnets, we often, people may think first and foremost of the magnets they interact with on a daily basis. Your refrigerator magnets. The kids, the grandkids come home, they bring a drawing. Boom, we put the magnet up, and we have our refrigerators decorated. But we're talking about something very different. We're talking about an electromagnet. And, many of you, I hope, will remember, doing little experiments in science class where, you take a battery, you take a coil of wire and wrap it around a nail. And that flowing electric current actually generates a magnetic field, and a very powerful one. And so it turns out, this technology that I'm showing here, battery and a nail and a piece of copper, is essentially the same technology that we have in our large toroidal field model coil, but on a completely different scale. So we're talking about electromagnets, and this is really required to generate very high magnetic fields. So those of you, what's a reference point? Those of you who've ever been to a hospital and had an MRI for medical reasons, you're sitting in a magnetic field of about 1 to 2 Tesla, the unit we use for magnetic field. What we're interested in with our magnet is to generate a magnetic field about 20 times higher than a Tesla. And many of the challenges that come along with doing that sort of scale like the magnetic field squared. So going from 1 Tesla to 2 Tesla, it's not that hard. Going from 1 Tesla to 20 Tesla, things get harder by a factor of 400, very nonlinear scale. So the next sort of, key lesson or primer lesson, if you want, is that modern superconductors enable small, low power, high field magnets. And I want to demonstrate that by looking at just some examples. And the first is that superconductors let us make magnetic fields with minimal power. When we use copper wire, like in that little battery experiment, we're running a current through it. And those of you who remember that experiment, that copper wire gets hot because it has resistance, electrical resistance to it. And it takes energy, your battery, for example, to drive that electric current through the magnet. And so if we were to look at 2 types of advanced electromagnets that we have operated here at MIT, one of which is this magnet you see here, all copper. You'll notice to make a field of about 12 Tesla for 4 seconds requires about 225 megawatts of power. That's actually the amount of electricity that you see in sort of small, urban, generating stations that are providing electricity to houses. So we have this massive infrastructure at MIT required to provide about 225 megawatts for only 4 seconds. If you contrast copper magnets with superconductors, a superconductor carries electricity with 0 resistance. That means the electricity can flow without any dissipation. We can build a much more impressive magnet that runs at much higher field for as long as you want, and we consume, about 2,000 times less power. That's really a good thing for fusion, because it means instead of consuming the power in the magnet, we're consuming it and selling it to make money. So superconductors, very important to make big magnets with low power. The other is that superconductors let us get to much higher magnetic fields than conventional copper magnets, and we can therefore shrink the size of our devices. So I like examples, as you can tell. And so this is a pretty good example. So we have particle accelerators that use magnets to accelerate beams of protons, let's say, for cancer therapy. And if we were to look at one of the original cyclotrons that used copper magnets, and look at this picture here, this was Lawrence's 84-inch cyclotron out at Berkeley, California in the 40s. His machine was massive. You can see the scale by looking at the team of people here, weighed about 5,000 tons. If we use superconductors, we can actually go to much higher fields. And you look at the picture at the bottom right, and you can see that essentially the same, capabilities in terms of providing a particle beam are given by something that's about 100 times smaller. It's 100 times, cheaper. It's 100 times easier to build, et cetera. And so superconductors really help us build smaller things with high magnetic fields, and to do that at low power consumption. The second lesson I want to give you is that fusion, so the types of devices that we build in magnetic fusion, always goes to the highest magnetic field possible. And you can see that in this nice historical view. So starting back in the 1950s, 1960s, we had copper wire. That was all we had to make magnets. Looked just like the little battery with the wire around the nail. And we had, fairly low performance, unimpressive devices as a result. And then what you can see is over the course of the next, 4 or 5 decades, we continually made advances in copper and then ultimately in superconducting magnet technology that that let us go to increasingly high magnetic fields. And so as we have approached much higher superconducting magnets, we now have a material, which I won't have time to talk about too much, but it's essentially a new generation of superconducting material that lets us think about going to even higher magnetic fields than have previously been achieved. And this is ultimately going to be the key to making fusion happen smaller, sooner, and at lower cost. And, why is that? So at MIT, starting about, maybe 10 years ago, we basically envisioned a pathway to get to fusion energy, power on the grid, in maybe something like 15 to 20 years. And the way that we would do that is by taking a lot of the plasma physics, a lot of the physics that we have done, and combine that with superconducting magnets to ultimately build a device that was much, much smaller than anything that had been previously envisioned. That would actually demonstrate, you can see that device here, that would actually demonstrate net fusion energy or producing more power out than in at a pretty substantial scale, making about 100 megawatts of fusion power. That's starting to look like the amount of power you'd want in something like an electricity plant. And if you could demonstrate this device, hey, we can make net energy from fusion, this starts to look something attractive to then go off and build a power plant out of. And maybe put something like 200 megawatt electric onto the grid. But of course, to build these devices, to make them compact and to do it quickly, we ultimately have to have the magnet technology to do it. And so while about 10 years ago, we had some ideas about how to use this new high field superconductor to make magnets, we didn't really have the scientific and engineering knowledge to take the step from these concepts to the full-scale fusion devices. And so ultimately, the project that we're going to talk about today, the purpose was really to act as a bridge between the concepts that we had and the devices that we know will produce fusion energy at very small size. And it basically gave us a pathway to do that. So that's why superconducting magnets are better for fusion energy. Much less power consumption. We can go to much higher field, which means we can make our fusion devices much smaller. And if we can make our fusion devices much smaller by a factor of, let's say, 50, that means 50 times easier to build, 50 times cheaper. Smaller organizations can build it. Instead of 30 national governments sponsoring a big science project, I can start to think about university scale or even company scale building net fusion energy devices. So these magnets are really the key. So now what I want to do is give you a sense of how far we were able to take this technology from, kind of concept scale about 10 years ago, ultimately in the last 2 years to really build a mature magnet that we think is ready to go into fusion. So what were we trying to do in this project? One way to think about it is that we were trying to retire certain technology and programmatic risks in building these kinds of magnets. So we sort of sat down and made a list and said, well, what are all the challenges that we think are out there? Let's design a program that's going to go off and kind of check the box on all of them in a relatively fast and low cost way. And so I list some of those risks that we were really trying to tackle, here on the left. So we had to figure out how to design these magnets. How do we take this material, turn it into a larger scale magnet? We had to work on things like supply chain. How do we get enough of this material? How do we get the structural materials? Can we get vendors to help us build these magnets? How do we fabricate them? We need tooling. We need manufacturing processes. We need to scale these things up so that a company like Commonwealth Fusion can go off and build a lot of them. We need to deal with the challenges of operating magnets at high field. Turns out when we operate these magnets at high fields, there's a lot of structural challenges. You get stresses and strains on these magnets as they attempt to contain the magnetic fields. We have a lot of operational challenges and a lot of scientific challenges about how we deal with the magnets during normal operation and during off-normal events. And so, in a sense, one way to think about the TFMC is if we were successful, we've sort of written the playbook for how to build and operate these magnets at full scale. So let's take a look a little bit at the magnet technology itself. So this is, again, a picture of the magnet, give you a sense of scale with people in the background. And what are some key sort of parameters of this magnet? So we'll talk about what turns are in a magnet. Essentially, you can think of turn like a little wrapping of copper wire. Every time you wrap copper wire around that nail, the magnetic field gets a little stronger. So there's 256 turns of wire of superconductor in our magnet. We used about 270 kilometers of superconductor in our tape. That's about 170 miles. So the distance between Boston, Massachusetts to Albany, New York. That's how long a single strand of superconductor would have to be. That is essentially what's coiling around in our magnet to make the magnetic field. We use a coolant called supercritical helium, essentially, helium gas at very high pressures, about 300 pounds per square inch or 20 bar, to ultimately cool the magnet down to 20 Kelvin, just 20 Kelvin, 20 degrees above absolute zero, so very cold. We put about 40 kiloamps of electricity in the magnet in order to generate those magnetic fields. To give you a sense of scale, your house probably has a 100 amp or 200 amp breaker box in the basement. So we're sort of talking about 40,000 times more electricity in this magnet than in your house. We have a peak magnetic field, as we said, of about 20 Tesla. We have a lot of energy that's stored in these magnetic fields, and the magnet is pretty beefy. It weighs about 10,000 kilograms, or maybe about 22,000 pounds. So this is a pretty impressive magnet. And many of these parameters that I list here have basically taken, a step of anywhere from 100 to 1,000 and even more in terms of what magnets were doing before this magnet was demonstrated. So this is really a big step forward in the technology. I want to peer inside the magnet just a little bit for those of you who are curious. So how do we make these magnets? So it turns out the way we do this is these single big magnet is essentially composed of 16 smaller magnets. So if you think about this thing that I'm showing here called a winding pack, this is essentially composed of 16 plates that we call pancakes. Within each plate, the superconductor spirals around. So it allows the current to go in that spiral and generate a magnetic field that's going through the bore. So we take 16 independent magnets and we connect them all together. We bolt them all together to form one big magnet. And what you can see here is we have the ability to inject electric current at the top. It spirals around one pancake and then it goes to the next pancake, spirals around the other, spirals around the other. And so essentially we're building up many, many turns. Think of it like many turns of copper wire to generate very high magnetic fields that are pointed in this axis. So once we have this sort of core of the magnet, what do? Well, we have to put it in a very large structural vessel. So these are some neat pictures of our structural vessel that we had to build to contain this winding pack. So you can see an example, one of the pieces of steel that we had forged and then machined, very specialized steel to provide high strength at cold temperatures. And once we have, this case, there's a lid that fits on top. We can take that winding pack, which we just looked at, which is what's carrying all the current, and we can essentially insert it into this case, put a few layers on top, and then ultimately bolt everything together to form the core of the magnet. Now, I mentioned at the beginning of the talk, this isn't just a magnet. So we actually have to go through and build a test facility. And so we took a room, you can see here on the top left, that was full of scientific equipment starting in January of 2020. In the span of about 8 months, emptied it out completely, polished the floors so we'd have a nice pretty place to do our magnet test. And then just about 8 months later, 9 months later, poof, we have a test facility. So it's hard to underestimate, how fast the team was able to move to turn, a room that was essentially full of power equipment into a world-class test facility. And of course, this test facility provides all the systems that we need to essentially build essentially test this big magnet. And I don't want to go into too many of the details, but we have vacuum systems, power supplies, cryogenic systems to help us cool the magnet, and all the big, gantry cranes and things that you need to move big pieces of metal around. So very nice. So, okay, so we've looked a little bit at both why we're doing this project. Why are we building this magnet? Because it makes fusion smaller, easier to do, cheaper to do, and hopefully shrinks the horizon and brings fusion energy a little closer. We looked a little bit about the magnet technology and what went into it, just at a sort of a glancing level. But now what I want to do is actually say, we've seen the magnet technology. we've kind of talked about how, many orders of magnitude it had advanced things, and the fact that it worked essentially the first time that we tested it. So what I want to do now is talk a little bit about why we were able to do this. Why was this done at MIT, and how were we able to do it? And, the spoiler to the rest of the talk, I think, is that there are three answers that explain how the team at MIT, with CFS and our vendors as partners, were really able to push this technology forward. And it's these three things. The first that I think many of you will know intimately as members of the MIT community is it's the culture. And culture is, I like this definition of culture. It's the pattern of behavior ingrained in an organization that defines how it solves problems, including beliefs, norms, values, and mindsets that shapes individual action, shapes what we do. And I think, many of you as MIT grads will recognize sort of this spirit, both from your time here and that, it was inculcated in you and you've kept it with you. And I go to a quote from Joe Minervini, who I talked to about this talk when I put it together. He was the former head of the magnet division here at the Plasma Science and Fusion Center. And what he said really summed this up for me. He said, in keeping with MIT tradition, we tackled only the most difficult technical challenges in the field of magnets. So we didn't do sort of run-of-the-mill research, small-scale R&D projects. MIT chose to characteristically, bite off really the most complex challenges that would have the biggest impact. And I think you'll see that in the history that we'll go through. The second thing, which I think is important, is this idea of institutional capabilities. And that's the intrinsic ability to move quickly, confidently, and at the scale required. And MIT is a place that goes really beyond university scale. You saw the pictures that I showed about what we were able to achieve. This isn't small benchtop science. And so MIT really has the sort of ability to do things that other places can't, to move quickly and to do things confidently. And that was really important. Rick mentioned at the beginning of the hour that I was one of the founders of Commonwealth Fusion Systems, a private company. Well, the reality is for the first few years, that company wasn't going to have the capabilities to do the things required to build this magnet as soon as possible. And so we needed to partner with a place like MIT that could do it. The other, and third and final thing I want to always point out is the people. So when we look at how such projects are completed successfully, it's really about the integrated experience and the expertise and the effort of the individuals involved in a project. And it's, again, as many of you know, the people at MIT is really the ultimate value of being a part of the community. They just bring tremendous energy and effort to the mission. So with that, what I want to do is tell a little bit of the story of our history at MIT and kind of explain in the next, let's say 10, 12 minutes, how we got where we are. And, the story begins about 100 years ago, actually. And so I think it's probably rare in one of these Cardinal and Gray societies for a story to go probably prior to any of the existing members. So maybe this is a first. But the story of how MIT was able to do this really begins in 1923. And it begins with this guy, whose name was Francis Bitter, who was a grad student sort of wandering the halls at Columbia and looking for an interesting PhD project. And he said, essentially I put a quote here. He said sort of the moment that started his journey was sort of spying this impressive looking magnet kind of abandoned in an empty laboratory, and sort of sparked his interest. And as he came to sort of understand how this magnet worked and what it was possible to do, he learned that it was really only possible for these magnets to go to about 2 to 3 Tesla, about what our modern MRI magnets in a hospital are able to do. And he sort of said, I want to study things that require much higher magnetic fields. How do I do that? So he sort of states here, the problem was discover how far was it practical to go in terms of building high field magnets. So in the mid-1930s, Bitter comes back to this idea and he joins the faculty at MIT and he really takes the first step. He came to MIT basically at the behest of Vannevar Bush. You see here one of the key policy and technology drivers in World War II, who was at MIT for many years. And Bush convinces Bitter to come and build the first high field electromagnets that use current without iron, magnetized iron to generate magnetic fields. So in the 1930s, Bitter builds this so-called magnet number 1, his first test that he's ever done. It'll be the first test of a high field magnet. But of course, remember, this is a copper magnet. And so it takes a lot of power to run because copper is a resistor. And so Bush pulls a few strings. And he basically gets Bitter the ability to go to the Scotia Street substation in Boston proper, go down into the basement, and during the off hours, use the huge power that they had available during off peak to test his magnet. And it turns out you can actually go and see that building today. So this is a map of Cambridge. Here's MIT along the Charles River. You can see the site where we tested our big magnet in 2021. And just 1.4 miles across the street is actually the original building, the Scotia Street substation, where Bitter tested his first magnet. And so I made my pilgrimage over to see the building. So you can kind of go and visit that site today. So this is the first time ever in this building that a magnet was tested above 2 Tesla. And it's just a walk down the street from the PSFC and MIT today. So what happens? So Bitter basically develops his technology and he figures out how to build magnets such that they have very high currents, very high fields, and ultimately figures out a way to cool the magnets such that they can perform at a very high level. And it turns out, what's the lesson for the magnet we built? Turns out the way we built our magnet is really not all that different from how Bitter built the first magnet almost 90 years ago. So you can see a picture here of Bitter's first magnet, where he has copper inside. You see that characteristic spiral that generates a magnetic field. And he says, well, I have to cool my magnet. So I'm going to put this magnet in a pressure vessel, pass coolant through it, and I'm going to keep my magnet cold. And it turns out this fancy magnet that we built today owes a lot to Bitter. We do the same thing. We put a whole bunch of plates that have that characteristic spiral that generate a magnetic field. We put that in a big steel vessel, and we pass coolant through that vessel to keep things cold. And so it turned out we learned a lot from Bitter's first magnet. He hit on these ideas 90 years ago, and that legacy very much still with us in how to build the best high field magnets at MIT. So following the development of these Bitter magnets using copper, a series of fusion machines, which some of you may know or have visited, was built here at MIT starting in the 1970s. And so a number of people from MIT were key in essentially turning high field copper magnets into the world's highest field fusion energy experiment that we ran at MIT for about 25 years, the so-called Alcator CMOD. And so you can see a lot of the people on the team at MIT and a lot of our sort of institutional legacy was involved in doing things like forging big structures, making big, super big structures that can support magnet systems. And of course, that experience from the people who worked on those programs translated directly into what we were able to do for our magnet project. And so you can see the idea of forging big pieces of metal, doing precision machining with vendors. And doing other engineering processes was something that we were able to import directly from the Alcator programs that ended just prior to our magnet program ending, so that we had a team of people who understood how to do this kind of R&D. And so this is a picture, just a couple pictures very quickly, to sort of show you what that Alcator CMOD fusion experiment looked like. So you can see very complicated engineering, very large scale systems that had to be put in place, complex assembly of very big structures. And so a lot of that experience is reflected here in the kind of work that you see being done at MIT to assemble the test facility and to assemble the magnet itself. So you can see a picture of that magnet be craned in. When you crane in a magnet that's in a program that's worth about $50 million, you want somebody like Dave Arsenal, one of our head technicians who's operated a crane for 30 years, to be the one with his finger on that button. It's the legacy of experience and expertise that's stored up at MIT that lets us do all these things. In terms of superconducting cables, MIT's been a center of the development of superconducting cables for a long time. Essentially, how do we take superconductor and put it into the form factors required to build big magnets? So you can see Mitch Hainig, Mike Stees, Bruce Montgomery. These are all people who worked at MIT in the 60s, 70s through the late 90s, basically figured out the first way to turn superconductors into magnet conductors that we can use to build these high field electromagnetic coils. And so, this translated directly today. Some of the first equipment, you can see the colors and a bit beat up. Some of the equipment that was actually used in the first ever development of superconducting cables in the 60s and 70s were used directly to build cables and coils for the toroidal field model coil program. So not only did we have the people at MIT, but we actually still had a lot of the same industrial equipment that was used. So we didn't have to buy it. We didn't have to go out and spec it. We actually had it in-house with people who knew how to use it, and we were able to just import it directly into the program. Now, I mentioned at the top of the hour this other program that we could compare to TFMC, the ITER central solenoid model coil. At the time, in the late 90s, this was a record-breaking superconducting magnet, largest superconducting magnet of its kind. And MIT actually had a key role in building that magnet. We built half of that magnet, and we did it here in Massachusetts. So the Plasma Science and Fusion Center actually rented a facility, a big warehouse down in Hingham, and we built up the ability. You can see big tents and fork trucks and big fabrication facilities. We built up these capabilities at MIT and learned how to build big magnets. And you can see here Rui Vieira, one of the chief engineers on that project. Here's a picture of him in Japan in the late 90s. Well, turns out Rui Vieira, who you can see down here at the bottom left, was my chief engineer at overseeing the TFMC project. And so, I like to point out it's no accident in some ways that these pictures look so similar, right? Big, complex superconducting magnet with people who really understand them. And so, having a whole team of people such as Rui means young guys like me with a lot of ideas and drive can come along and work with people who have really deep expertise and knowledge about how to make systems like this, but more importantly, make them work the first time out of the gate. We have other things. So I mentioned this new high temperature superconductor that we used for the TFMC magnet. Really the secret material, if you like, or the special weapon that makes the whole thing work. Well, it turns out, starting about 15 years ago, people at MIT were some of the first people to have ever worked with this material and started to think about how to put it into cables, again, that could be used for fusion magnets. You can see some of the early prototypes and some of the early ideas and tests that were done about, starting about 15 years ago to work with this material. And of course, traditional MIT fashion, the rest of the world is now using some of the lessons that we developed here to build their own superconducting cables. But ultimately, we were able to use these technologies and the in-house experience to build all of the cables and superconducting things that we needed to test the toroidal field model coil. Similarly, there's other magnet technology. We don't really have time to go into too much detail here, but essentially the way that this magnet was designed and operated was based on a concept that was developed here at MIT about 15 years ago, a very novel way, in some sense, to build high field magnets. And so you can see two of the people, Yuki Iwasa, who's been here since the 1960s, Dongkun Park, who's one of the new, sort of younger generation of magnet engineers like myself. We've been building these magnets for a long time. On the bottom right, this is actually an interesting timeline. So you can see year versus the progress in building much higher field magnets. And of course, you can see who started it. It was MIT. And MIT actually led in this field for many years, sort of in the race to build high field magnets. And again, we've had impacts far beyond MIT. So there's a lot of institutions out there now using the technology that MIT came up with to develop these high field magnets. And of course, we did a lot of that work ourselves internally. I'm going to skip a little bit to the end. I want to make sure we have time for questions, but I also want to just point out here that a group of people, including students, myself at the time, about 15 years ago, started to really think about building large-scale magnets out of this material. And so in some ways, the magnet that we built and tested a year ago, we were, myself and a group of key people already thinking about it about 10 years ago in some of the academic courses that we took at MIT. And so, there was a lot of sort of thought process about how to make these magnets successful. And of course, we have other partners at MIT, other places at MIT that do big scale science and engineering work that we were able to utilize to bring together to help us build this test facility. There's obviously a lot more things I can't possibly cover in a talk like this, but basically just putting some things up here to show that MIT has really played a long history and an important role in a lot of the development of magnet technology for fusion, for medical physics, for particle physics, and many other fields and industries. So I think I want to end there. We're about on time. We have about 15 minutes left. And just say that I hope what I've been able to do is show you why high field superconducting magnets are important and why we want to use them to bring fusion energy much, much closer, to get there faster, do it at lower cost so that we can use fusion to get to climate change. We don't want fusion to always be 30 years away. But ultimately to do that, we had to develop in a very short period of time a large step change in how good our magnet technology can be. And ultimately, how are we able to do that? It's really this timeline here, starting from, essentially Bitter coming to MIT in the 1930s, all the way to us testing our magnet in 2020. Yes, there were many important individual steps along the way, but it's really that long arc, that 80-year arc of sort of institutional capability, expertise, and people that let MIT execute on this scale and to get it right at this speed in a way that is very unique in the world. And I think everybody who's on the call sort of knows those qualities of MIT and has been a part of that culture. And so I hope I've convinced you that we're doing good work in magnets and that the magnet advances we're making are going to hopefully bring us closer to fusion energy in the near term. And that MIT is really the institution where things like this are possible. So with that, I will say thank you. And I look forward to interacting on questions. Hey, Rick.
Thank you very much. I was particularly struck by your insertion of references to culture and to history. We don't see that very often in Cardinal and Gray programs, and it's certainly a testimony to the fact that you personally have inculcated the MIT philosophy into your professional identity. Relatively few years, but you've obviously bought into it, and we really appreciate that.
Absolutely.
The one thing to get started with, I was having a little bit of cognitive dissonance. The material describing your program talks about high temperature superconductors, and yet you also talked about 20 degrees Kelvin. Is 20 degrees Kelvin truly high temperature?
It is actually. So the previous generation of superconductors worked at 4 Kelvin, 4 degrees above zero. So now, okay, you say, hey, Zach, hang on. High temperature superconductors at 20 Kelvin, that doesn't sound like a big difference. It turns out that even though it's 20 Kelvin, very cold, the difference in things like material properties from 4 to 20 Kelvin is enormous. So let's take an example. We like magnets to be cold. So we need to remove heat from them. And the difference in things like the thermal conductivity, how fast does a material move heat through it, goes up by a factor of 4 when you go to 20 Kelvin. The specific heat, how much energy does it take to raise the temperature of a material, goes up by a factor of 80 when you go to 20 Kelvin. And so even though that temperature difference, only 15 Kelvin, it makes the engineering and operation of these magnets completely different than the previous generation of superconductors, because things like material properties are changing by a factor of 100 in a way that's beneficial to you, the designer, and the magnet operator.
If we're talking about going to market, is 20 good enough for engineering purposes to actually take this ahead? Okay, that's really the critical question, I would say, from a business point of view.
Yep,
okay.
Absolutely.
Please, ladies and gentlemen, type your questions into the Q&A box, but I will get started. Let me start. Dick Kane asks, how does one energize a superconducting magnet?
Great question. In the same way that we would a normal copper magnet. Essentially, remember that picture? We have the battery and the little wires, and we have the turns that make the magnet. It's the same thing for a superconducting magnet. So you have a power supply. In our case, it's a 50 kiloamp power supply. It's connected to the terminals of the magnet through copper and superconductor, and we drive current through it. Now, there's a trick, which I didn't talk about. I didn't have time. And this is the trick with superconducting magnets. You somehow have to get 50 kiloamps of current at room temperature to 50 kiloamps of current at 20 Kelvin without a giant bar of copper bleeding heat out of your cold system. And so we developed a very special piece of equipment called current leads here that effectively allow you to transmit 50 kiloamps of electrical current from 3,300 Kelvin room temperature to 20 Kelvin with almost no heat leak, which is a pretty impressive piece of technology. So other than the current leads, it really, you energize it the same way you do a conventional magnet.
Fascinating, that description of temperature. Barry Gloger asks, have you built sufficient magnets to complete Spark?
No. So right now, a lot of this work has now been taken out to Commonwealth Fusion Systems. So they're an independent company from MIT, and their job is really to essentially manufacture the magnets for Spark. So they have a site. It's about, say, 30 miles west of Boston in Devons, Massachusetts. And they're about to open what they call the magnet factory, where they're going to be producing all of the magnets for Spark. So the key thing that we at MIT did, what do we do? We're not manufacturing people. Our job is to be researchers. We do first of kind things. We solve really difficult problems that nobody's ever solved. And we've done that in many ways. And our job is to say, hey, guys, here's the recipe. We want you to go off and figure out how to make this efficiently, how to optimize it, and ultimately how to produce many of something. That's not really our expertise here at MIT.
Larry Pleskett asks, what is your estimate for the time scale of usable fusion energy? How likely is this to happen ever? And I say that because as a Cardinal and Gray member, I too have lived through the generation of fusion energy is 20 years ahead and always will be.
Yep. Yeah, I think it's a really important question. I think the most important thing that we can do now is to lay out a pathway to get there and be held accountable to that pathway. So MIT and CFS about 5 years ago said, in 3 years, we're going to build and test the magnet technology required to demonstrate this device. We're going to have a site to build the machine, and we're going to have the physics basis done that shows this machine will work. 2021, check, check, check. All three of those things done. CFS raises $2 billion based on that success and is now in the process of building the machine that will tell us if we can get net energy out of fusion. So they're predicting that will be done in the mid-2020s, and we should all hold ourselves and CFS accountable to that. And if that's successful, we take the next step to putting energy on the grid in the 2030s. I think that fusion is a very high risk but high reward technology. And so it's not something that we want to put all our eggs in that basket. It's part of a much broader development to tackle problems with climate change, greenhouse gas emissions, particulate emissions, et cetera. But I do think we're now at the stage where there is a number of things happening in the field of fusion. We probably don't have time to go into it. Investment, private companies, industry, significant changes in government from science to engineering to industry translation, where we are within 10 to 20 years of seeing watts put on the grid for fusion or not, which in some sense is a good thing. If fusion can't put watts on the grid in a way that's economic, which we ultimately have to go out and show, then we should be moving on to other energy technologies that are going to produce the kind of energy we need as a society. So I think we're actually within 10 to 20 years of seeing a yes or no answer.
It turns out that me and several other people have the following question. Why are these things D-shaped and not more symmetrical?
Great question. So if you let's take a piece of wire, it's kind of a floppy piece of wire, and we'll put an electric current into it. It turns out that the magnetic field that's generated by that loop of wire will interact with the current to create a force. It's called an I cross B force. And so the result on this floppy bit of wire is that the forces will point radially in all directions, and it will relax that wire into a perfect circle. So I now have constant tension all the way around this magnet. Now, that's true if I have a single, a circular shaped magnet or a long solenoid. I have these hoop forces. In the toroidal field magnet, which is a solenoid that's bent all the way around into a donut, the magnetic field structure is a little bit different. And it turns out on the inner side, there's actually some pressures that mean that the state of constant tension that magnet likes to sit in is not actually circular. You have something pushing here. It actually likes to sit in a D shape. Instead of a circle, it likes to slightly relax into a D shape because of the slight differences in the forces due to the geometry.
Thank you. Rod Walker asks, how many magnets needed for the 2025 power generator?
So the magnet that I showed is one of about 18 that need to be built to create that toroidal field magnet.
Rod also asks, how can I invest in Commonwealth Fusion? I'm not sure you can be in any position to address that, but if you want to take a stab, quick.
If you want to invest in CFS, you can always reach out to CFS via their website.
Okay. Fred, no middle name provided. Why did you select the present size of this unit? I.e., what are the issues associated with making a magnet half this size?
It's actually a really important question. So what we did when we set out to retire all those risks is we said, we have to retire all these risks, but we want to do it fast. We don't want to spend a ton of money. And we want to do it in a facility that's about MIT scale. But what we learn has to extrapolate to full scale if we don't do it at full scale. And it turns out we were pretty clever in essentially figuring out how to retire all of these risks in a magnet that's about 50% of the scale of the final one. And you might say, well, isn't scale a problem? Well, turns out the magnet was big enough that the vendors that we used, the techniques that we used to produce it, are simply just scaling it up. Instead of machining a plate that's this big, it's making a plate on the same machine that's just a bit bigger. And so in some ways, there's really minimal risk in scaling that up in size. So that was a really important aspect of doing it quickly, getting the right answers, but still having confidence that when we took the step up to scale, we don't introduce any new problems.
Thank you. Larry Smith, assuming the 20T magnet technology challenges are all solved, what are the most significant other challenges standing in the way of fusion energy being adopted?
Great question. I'd say there's three. The first is we want to run for long periods of time. So obviously, if we're going to make a power plant, it's not good enough to run for 5 seconds, 10 seconds like an experiment. You've got to run for months in order to do that. So that's the first technological challenge. There's a lot of ways to do that, but we got to do it. The second is fusion plasma is about 100 million degrees. It's constantly shedding heat that has to be exhausted through physical structures. And so heat exhaust is a very important challenge. We have to make sure the materials don't melt and other things. And the third is some of the nuclear technologies that we need to produce power. How do we turn fusion energy, what's going on in the plasma, into electricity? Now, a large part of those challenges have already been solved by things like nuclear power, but for fusion energy, there are some subtleties in the engineering technology that we have to address.
Viva Brecker, how is the TFMC shielded to protect nearby conductor metallic cables and structures from induced eddy currents as the high field comes on? Did the magnet accidentally quench? What happened?
We could have used you on the Safety and Operations Review Committee. Thank you for the question. So the biggest thing that we did, this is another reason that MIT PSFC is amazing, is we had, you saw that hall that we cleared out. It's a 10,000 square foot hall. It sits right on Albany Street. Students walk by all the time. But the hall is big enough and the magnet was located in a specific spot such that the fringe fields didn't actually go out into public space. But we did do this in a building where we have iron girders supporting the roof. And we actually had to do calculations to make sure that we weren't inducing magnetic fields. We weren't pulling the roof in. We weren't going to suck wrenches from around, combined with very careful protocols about magnetic fields. So we did have to worry about those questions.
And I'm afraid we are running close to the end. We have one more interesting twist here. Are we dependent on, Fred asks, are we dependent on China for the rare earth components in the superconducting cable?
We aren't at the moment, and it turns out the amount of rare earths that's in the superconductor is tiny relative to the rest of the base materials that are in this material. It's about 1% of the material. So we have a lot of different sources to do, although China is probably an important one. But the nice thing is, in order to build these types of materials, it's a relatively tiny amount of rare earth.
Ladies and gentlemen, one of the criteria that I always use when we come to the end of these are there still lots of unanswered questions? Regretfully, there are, which is good, but it's also bad if you ask the question. My apologies. But right now, I'm going to have to wrap this up. Zach, I thank you profusely. That was an extraordinary insight into an issue that so many of us are wrestling with, and frankly, so many of us think of might be the best solution to the energy crisis that the world is no doubt addressing. And there's the folks, for example, in Egypt are hassling over even as we speak. So again, thank you. We're going to bring this to a close. Ladies and gentlemen, appreciate your attendance. I look forward to seeing a number of you next week or next month in Wellesley at the Country Club for our holiday party. And then right now I say good evening, good afternoon. Thank you. Bye-bye now.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.